So let's imagine that we have a system of springs. So here is a spring, and it has spring constant K, and it's fixed at a wall here. And then we have an object of mass m that can slide on some frictionless horizontal surface. And that is also attached to another spring, and that also has spring constant K, which is then attached to another object of mass m that can also slide without friction on a horizontal surface, which is then attached to a spring, which is then attached to the wall and fixed as this one is. So let's say that these are the equilibrium positions, and we can move this object right or left, right? So if we move it such that it's there, then we can say that there's an x value or an x1 value for that object from here to there. That's x1. The same thing with this one. We can move it this way or that way. The displacement of this object we'll call x2 from its equilibrium position. So let's construct the Lagrangian and the equations of motion. So the kinetic energy just involves the velocities of these objects. So that is, they have mass m, so we have m over 2 x1 dot squared plus m over 2 x2 dot squared, and the potential energy involves these springs. So when we stretch or compress these springs, we get potential energy. So it's 1/2 k times the stretching or the compression, one way or the other. We call that x1 squared, plus we have the same thing for this one, right? So if we have this one is moved by an amount x2, then this one, if this object moves to the right by an amount x2, then this spring is compressed by an amount x2. And if this object moves left by an amount x2, then the spring is stretched, but we always have 1/2 k x2 squared. But what about this one? That's going to involve the difference between x2 and x1. So we have 1/2 k times x2 minus x1 squared. And so the Lagrangian is k minus u, which ends up being m x1 dot squared over 2 dot squared over 2. See, we have minus 1/2 k x1 squared. Then we have minus k x2 squared over 2 and minus k over 2 x2 minus x1 squared. Now we need to evaluate d by dt times dl by dx dot dx1 dot minus dl by dx1. That has to be equal to 0. And of course for dx2, the same thing. Oops, I made an exponent now. Okay, so we'll evaluate those two equations, and we'll get dl by dx1 is, of course, minus k x1 plus k x2 minus x1, these can be combined into, let's see, k times x2 minus 2, x1. We have dl by dx1 dot equals mx1 dot. And for the dl by dx2, we have minus k x2 minus x1 minus k x2. We can combine these two into k x1 minus 2 x2, and then the dl by dx2 dot is mx2 dot. So our equations of motion, let's combine these, and our equations of motion become mx1 double dot, so that's ma for the object on the left, is equal to k, of course, it's the spring force that's involved, x2 minus 2 x1, and mx2 double dot for the object on the right, that will be k times x1 minus 2 x2. So we sort of see a symmetry there, as we would expect.